Um, Thanks, Matt. My name's Amy Vale. I'm the district supervisor in the Cadillac District Office for drinking water, environmental health. Before I came to Eagle, I did work in and run drinking water laboratories and wastewater laboratories for over a decade. So I get the job to do the laboratory analysis presentation. So I just wanted to start off by kind of talking about what I'm going to discuss in the next kind of 45 minutes. When we talk about laboratory analysis, there's a lot of different areas where we're taking samples and having them analyzed in a laboratory. So we have our compliance samples that a lot of time we're taking and shipping out to different labs that have, different capabilities. We have a lot of our bacteriological sampling that we do. That in itself could be a whole presentation. And then we kind of have the stuff that you're doing on a day-to-day basis for either like plant operations and process control to see where things are at, or for reporting on your monthly operations reports for compliance. And that's kind of what this presentation's about. So I'm going to cover a variety of topics, and I have them listed here for the most part. And then for these, each different analysis, I'm not really going to talk about step 1, do this, step 2, do that, step 3, do that. I'm going to talk more about the test in general, some of the pros and cons, some of the things that can go wrong, and some of the requirements under the different methods. So, hopefully if you're doing these in your job, you've been taught by, skilled professionals, and the hands-on stuff, what you should be doing. But this is to kind of help why you're doing what you're doing and what issues you might come up against. So what I did with this presentation is I kind of took all the methods for each of these and that are approved in standard methods, and I'm going to discuss, kind of the more common ones. So we're not going to go through every single one of these. So for like chlorine residuals, there's a lot of different approved methods. Most of you are probably familiar with DPD colorimetric, which I probably, most people use, which is like the hot colorimeter. But there's also different methods out there which are more precise, such as the titration methods. So with those, you're doing, specific amounts of an acid into the sample with a base and looking for a reaction. Sometimes DPD titration is using the same exact chemicals that you use in the colorimetric method, just doing a titration that way. The amperometric titration is using electricity, like looking at the resistance when you're doing the titration. So you're looking for an electrical change. Sometimes you're using a pH meter with that one. Iodometric methods are using iodine as your main part in the method or the test that you're doing. There's a titration and electrode method. The electrode method is only for total chlorine. And then there is the FACS, which is the shortened term, and that is using a different type of chemical that's listed down there. I'm not even going to butcher it. And that is only looking for free chlorine. But I'm pretty much going to focus on the DPD method of colorimetric because I would say probably 95% of you will be using that one. So for the DPD colorimetric method, DPD stands for N-N-diethyl P-phenyl N-diamine. So we call it DPD because that's just a little less of a tongue twister. And there's pretty much two different types of ways that you can look at it. We have the color comparator, which is the old color wheel, and we have either a spectrophotometer or a colorimeter. They both work pretty much in the same way. They're just different types of, equipment that you're using depending on what you're doing. But for, every one of these, we're looking for a color change from clear to the darker the pink red color means the more chlorine is in the sample. With both methods, there's some things that you should take into account and think about. One is when you're looking at what type of chlorine you're looking for, how, what you should be timing it out at. Both if you're looking for free or total, I'm going to say total coliform, I don't know how many times, chlorine, you're going to have a different type of reagent depending on which test you're looking at. So free, you're going to look for your results within 1 minute of putting that reagent in there and shaking it up in the sample. So, 1 minute to 2 minutes, you don't want to go any more than 2 minutes. So, pretty much immediately you want to be taking that reading because we're looking for that free chlorine that is out there and can still be used as a disinfectant and is not bound up with other things. Total chlorine, I got it right that time, is a little bit longer. It's 3 to 6 minutes because we are looking for chlorine that's free, but we're also looking for chlorine that might be bound to other, constituents in the water. And so it might take a little longer for that reaction. One thing to note is that it's good practice to use a different cuvette for each one. So we always had one that was labeled F and one that was labeled T because the reagents, the free and total, can react with different things in the water. And so you want to make sure that you're only looking for, if you're only looking for free or you're only looking for total. And if you have some residual in the cuvette and it reacts with more things in the water, you might look like you have more free chlorine than you do. You also want to make sure that you have blanks that you're using every time for these tests. You always want to blank with the water that you're testing because the water that you're testing might have some discoloration if you have some iron in it, or it might be cloudy or, what have you. So you want to be, testing like with like. When you run a blank with the free or the total reagent and you run a sample with it, you're comparing the same two sources. And so when you run that blank in the colorimeter or in the color wheel, you're saying this means it has nothing. So even if it's a little yellow tint and then your sample has a little yellow tint, the machine will pick up that, originally the little yellow tint meant nothing. So you want to make sure that you're always blanking with the water that you're testing. Didn't want to go that far. And so sometimes, people will use distilled water for blanks, and that's not a good thing to do because you're not testing like with like. So if you say distilled water, this means it has nothing in it, and then you test a little bit of a cloudy water or discolored water, it might read that it's actually got higher chlorine in it than it does. Again, the cuvettes are important because, like I said, trying to separate a free and a total cuvette. So in case there's any extra powder in there that you didn't rinse out, you're not getting false readings from that. You want to make sure that your cuvettes are, scratch free and, dry when you do the analysis. And, when you do these tests, there are QA/QC checks available. Most of the units come with this one, either not really calibrated or pre-calibrated from the factory, but you don't always know how long those calibrations last. And with these, unlike other methods where you calibrate on a daily basis or every time you use it or quarterly, these you really don't calibrate after you get them. They come factory calibrated and you can use them so many times. I think for the colorimeter, they say about 5,000 readings, and they're good for that. And then you pretty much buy a new one most of the time. So you can check to see how well those calibrations are still holding. There are standards that you can buy, like a 1 part per million chlorine standard that you can get. There's also little ampules of chlorine that are like 30 parts per million, and then you dilute it down and you spike a sample with that to see what's going on. So you can buy checks to check those calibrations. So just kind of talking about the difference between the color wheel and the colorimeter or the spectrophotometer. Color wheel, we call it a color comparator. Pretty much what you have is this color wheel, and you do a blank and then you put your reagent in and you just compare what's in your sample with the color on the color wheel. And the darker the color, it's got like what the readings are. This is, so many parts per million. This is so many parts per million. They're cheap. They're easy to use for the most part, but they do have some downfalls. So some potential problems with these is that disc that I just showed you. that can fade, and it can fade really easily because a lot of times people have these in their trucks and they have them, they're carrying them around with them. And so if they're exposed to the sun, if they get left out on the dashboard, these will fade. And so you won't get accurate readings because you're just comparing what you see. So, heat, if the chemicals get spilled on it, just over time, they just kind of deteriorate. So if you are using a color wheel, they say they should be, calibrated, which means compared to something So take one of those standards and see, does that 1 part per million standard, is it the same color as the 1 part per million on the color wheel? If not, get a new one. They recommend that they be replaced every 6 months, as a just way to operate. You could have expired or bad DPD reagents. So if the DPD reagents are discolored or clumped, you should get rid of those, or expired, you should get rid of those because that will affect how much of a reaction that you have. Since this is using human sight, what one person sees as, oh, this is, what I'm looking at. Another person might see, well, this is what I see. These two look the same. And so, depending on who's reading the test, you might get different results. And there's also interferences that can react with it. So again, colored water, high iron or oxidizing agents will make it appear to be a different color. So you want to make sure that you're dealing with that. A lot of places will still use these color wheels again because they're inexpensive. A lot of my small systems use them because they can give them to a maintenance person and they're not expensive and they can use those on site. But, for the most part, I can't believe we even still allow it, to be honest with you, but we do. Kind of the better one, the more accurate one, the more consistent one, but the more expensive one that more people will use is the spectrophotometer or the colorimeter. The main difference between these two, a spectrophotometer tends to be a benchtop unit that you have, some Hawk test in tubes or, just a benchtop spectrophotometer, whereas a colorimeter tends to be what we refer to as like the handhelds that you take out in the field with you, which are a lot less expensive and easier to use. So most systems use these colorimeters. Again, some of the issues with that price. So if I remember correctly, one of these, units was probably about $500 when I was in the lab. So now they're probably, 800 plus. I'm not sure. I haven't ordered one in a long time. But they're still affordable for lab equipment. If you start looking at some of these spectrophotometers, they're running in a couple thousands. So again, they're more consistent because you're taking away operator error. You have pretty much what it is in there, a beam of light shines through and it hits a detector. It's been calibrated to say if this much of the light goes through, this much of it was absorbed, that means it's 0.5 parts per million. If this much goes through, it means that much was absorbed, it's 1 part per million. The darker the color, the more light's absorbed in the sample, the less gets to the detector, the higher your reading. There are issues here too, and since this is electronics, there can always be more issues. We have issues with batteries because these kind of last a long time. People don't tend to change out the batteries and the batteries can corrode, especially if they're around a lot of different chemicals. Again, we're dealing with glassware. So we have, cuvettes that can get scratched. We have transmitters and receptors in the unit itself. So if you're carrying it out of the truck and you drop it, that could knock out some of the electronics internally. So those can be some issues. I think I want to talk about it real quick. Some of the things too to remember with these is there's different types of these colorimeters. So there is low range, mid range, and high range. And depending on which one you're using, there are different reagents that you use, different cuvettes that you use. So low range is the one that we typically use in drinking water. It's about 0.2 to 2 milligrams per liter. That uses a 10 mil pillow powder packets. There's a mid-range that is like a 0.05 to 4, I think. And that uses 25 mil pillow packets, but still 10 mils a sample. And the high range is either 2 10 mils packets or 125 mil, but it has a different cuvette. It's a plastic cuvette with a shorter wavelength or like length that the light goes through. So you want to make sure that you're using the correct reagents for the correct colorimeter that you have. So I just want to note that there's a difference. And you can tell the difference. A lot of times it says right on it like LR for low range and MR for mid range. And a lot of them you can switch between one and the other right on the unit. And the low range and the mid range, everything will read with 2 decimal points. The high range only has 1 decimal point. So these are kind of the more common ones that you would see in your you use in your treatment plants. So a lot of them, if you're a surface water treatment plant, have these inline ones that give readings, and they will put them to your SCADA system, and so they're pretty hands-off for the most part, for like your entry point and things like that. And then when you're out in the distribution system, these handheld ones are typically the ones that get used. Just know, I know a lot of times with, I think just the handheld ones, if you're at a really low range, sometimes the total and the free will tend to flip-flop. And you should always have a higher total than free, but at really low concentrations, sometimes it's inaccurate and they'll flip. So that is something that does happen. All right. For pH, there is only one approved method, which is the electrode method, which is pretty much a probe connected to some type of meter, and you get a reading. So it's a pretty easy method, not a lot to it. Some of the things that you should think about though, the electrode is kind of like your main thing that you're using, and so you want to make sure that everything is working with that. There's things to think about with storage. In the method, it says that you are supposed to store your probes in potassium chloride. I know some people like store it in distilled water or in like the pH 7 buffer, but in the method itself, potassium chloride is specifically laid out. So that is what you should be storing it in. So a lot of times when you get the pH, it'll come with a storage, storage liquid, and you just look at that and make sure it's potassium chloride because that's following the method. You want to make sure that you're maintaining your probes the proper way. Just look at the manufacturer's recommendations on what you should be doing with that. Filling solution. So if you have probes that you have to refill the filling solution, you want to make sure that you're looking at that and filling it, when it starts to get low, because if it gets low, that's going to create issues with the electronics and the millivolts coming through the probe itself. If you have a hole that you're using for filling or a hole in the probe at the top, don't cover that up. A lot of people will cover that up because they think it's not supposed to be there. And sometimes they're shipped with rubber around that hole, but the hole is actually there for a purpose. Not only is it for filling, but it's also for exchange of air and so that you can get proper exchange of things when you're using the probe. So it's supposed to be open. For what we're dealing with, you want to make sure that you have 0.1 units of accuracy, which most pH probes have that or even better. But that's kind of like the minimum. And as far as calibrations go, if you're using the probe daily, you want to make sure that you calibrate it every time you use it, at least that once a day. If you have probes that you don't use often, they might be a backup probe, or, if you're not doing pH in some part, every day, you want to make sure you're at least monthly calibrating those just so that you can make sure that they're still in working order. So if you're doing daily readings, you want to make sure that you're calibrating those daily. And then when you're doing those calibrations, you want to look at the slope, which tells you if you're using like a 4 and a 7 and a 10 buffer, it tells you kind of like how well they're in line with each other. And like 95 to 105% is the best. Some manufacturers don't spell out like what the slope is, what the range is, but nothing less than 90 to 110 should be, acceptable, but 95 to 105 is the best. Once you calibrate your pH meters, you want to make sure to check that. And so like with anything that you're doing at calibration, you want to make sure what we call is standardizing it. So taking a known buffer and checking it. So do your calibration and then taking a 4 or a 7 or a 10 and looking after I calibrated it, does that read what it said it should read? And if it doesn't, recalibrate it. And if you're still having issues, it might be the issue with your probe, it might be an issue with your buffers, but it's always good to check after you calibrate every time. When you're doing readings, you want to make sure that you're rinsing in between uses so that you're not contaminating the next sample with what was the previous sample. For the most time, we're dealing with drinking water, so it's not something that's really different from one sample to the next, but I came from the world of wastewater and drinking water, so you could really contaminate a sample. But you want to be as accurate as possible. So rinsing in between is good practice. And then when you're using the probe too, a lot of times since we're stirring the sample, you want to make sure that there's no air bubbles at the bottom of the probe. So if you just give it a little flick, if there's any air bubbles that are getting entrained because it's in a vortex, that'll go away so you can get accurate readings and the liquid is touching the probe. And this magnetic stirrer that you use, you should always use one to keep the sample continuously moving so it's homogenized. You want to make sure it's not too fast because it can actually create heat, and heat affects pH. So as you increase the temperature, you're going to change the pH. A good way to get around that, a lot of times they have like a silicone pad that you can put here that'll like not make the heat go. Or when I was in the lab, we just used like the scrubbies, the green scrubbies, so that would kind of dull if any heat was coming through. So you want to make sure that the stirrer isn't going so fast that you have water shooting out and everything, because that can cause heat issues. Along with your probe and your meter, you're going to use buffers and standards. So with these, you just want to make sure that you have daily, use new ones every day. I know sometimes in plants you are doing multiple pH readings during your shifts, but you want to make sure that you're using new ones every day. I've seen where they have them poured out in like a little plastic container over the top that will kind of keep dust and stuff from getting in them or any other kind of chemicals. Like I said, you can buy specific pH electrode solutions, which is that potassium chloride that you're supposed to store your pH in. It's good practice just when you get these buffers to date when you got them, date when you opened them, because I have seen, even though they all come with a certificate that says quality control, quality assurance, checked, we have gotten buffers in the past where all of a sudden nothing was calibrating correctly and I couldn't get anything to read, and I called the company and sure enough, that was a bad batch of buffer. They hadn't gotten recall information out yet, so it can happen. So, and you want to make sure you're not using expired standards or buffers. They're pretty cheap, so yeah, don't use expired stuff. When you're running the samples, just some things to think about. You want to run the sample immediately. So within 15 minutes of collection, because as I said earlier, with spinning it too fast, temperature affects pH. So over time, as that sample starts to warm up, the pH is going to start to change. And so you will not have the original pH of what you're trying to find out. So, you want to have accurate results. All right, temperature. So as far as temperature goes, you're going to do temperatures various places in your laboratory, whether you're taking the temperature of the water itself, whether you're using incubators to incubate stuff and you want to see what the temperature of the incubators is, if you're using water baths. So just a couple comments on temperature. One is making sure that you have the right thermometer for the job. So there's two types of thermometers. There's partial immersion and total immersion. Partial immersions tend to have like a line on them that says pretty much put me into the liquid up to here and I will, give you the temperature. Total immersion ones are those ones that you see like this. So they are either in some sand, or a lot of times for the incubators, they are in a liquid, a glycerol usually. So they're made, this just keeps the temperature more constant. So they're in this liquid or the sand, and they're in the unit that you're taking the temperature of. And so you have less fluctuations. But you can't always have that happen. Like your water baths, most of the time you can't immerse the whole thermometer in there. So you would have a partial immersion for most of those. You want to make sure that you have the proper graduations. So things like water baths and incubators, if you're using it for total coliform, you're supposed to have plus or minus 0.2 for a water bath and plus or minus 0.5 for a incubator. So you want to make sure that you have the graduations small enough that you can do that plus or minus. And you want to make sure that you can read what is between these things. So, somebody's not inaccurately thinking it's 0.1 and it's 1, or, and vice versa. So you want to make sure that those graduations, what the scale is. It's good practice to, look at these thermometers over time and look at how the temperature can change. I know certified laboratories have to either send their thermometers in to basically not have them recalibrated. It says recalibrate here, but they compare them to a NIST certified thermometer. And then they kind of give a variation. Is this thermometer reads like either like 0.1 higher than the NIST, which is a specifically certified thermometer. So then you could use that thermometer in the future. You just need to know that every time you take a reading, it's 0.1 higher than what the reading is. And usually they'll have like some type of tape on the thermometer that tells the staff how to, do that. Or you can replace them annually. They're not very expensive. So depending on how many you have, it might be cheaper to just replace them than send them in and have them compared against certified thermometers. I talked about the scale, making sure that you're reading the scales correctly because they're all different on different thermometers. And when you first get thermometers, a lot of times there is a gap in the liquid. And it's just from when, it was manufactured or what have you. So it's good practice to take that thermometer and, either put it in some boiling water to get the column to go up and fill in any air gaps that might be there. Because if you don't, those gaps will be gaps in the reading. And so you'll get inaccurate readings. Some people will just shake them out to try and get them to kind of condense back together. But, I always just boiled some water, and most of these thermometers don't read that, don't read up to boiling water temperature. So the liquid would go up and connect. Again, where you put your thermometers and what you have around your thermometers is important. So if you have an not autoclave, a incubator that has multiple shelves, if you're a certified laboratory, you're supposed to have a thermometer on each shelf because each shelf could have a different temperature. So that's always good practice, especially if you have larger incubators, because the temperature at the top might not be the temperature at the bottom. And so wherever your samples are, you want to know what temperature those samples were at. If you just have one central thermometer in there, you could be off by, 0.5 degrees or 0.25, 0.2 degrees, and that might make your sample out of compliance if you are a certified lab. You always want to kind of check and see if things are giving you background interferences. So if you are jam packing an incubator with a ton of samples, it's going to take a while for that incubator to come back to temperature. It's going to ramp up in temperature to start off with, or cool down because it's trying to like bring those samples up to temperature. So it could be really inaccurate results depending on what you have in there and when you're pulling your samples out. So you want to make sure that you're being as accurate as possible. All right, alkalinity, the only method that is approved is titration. And pretty much if you're unfamiliar with titration, what a titration is you'll have a sample of your water that you want to know the alkalinity or the hardness or something else on it. You'll put some type of indicator in there. So it usually is something that's going to change color as the pH changes. And then you'll use something that is known, usually an acid, and you will add a set amount into that sample and look for a color change. And when you see the color change, that tells you that it took this much acid to change, react with what I'm looking for in the water and change the color. And then you can do your calculations based on that. And, if it took 5 mils of acid, you can do the calculations. It'll tell you how many mils of alkalinity you have or how many, mils of hardness you have. So it's just using an acid, an indicator that changes, as you add the acid to tell you to do some calculations. For alkalinity, what we use for the acid, you can use sulfuric or hydrochloric acid. That'll be what you're titrating in. We use pH sensitive dyes, color dyes. So as that sample gets more acidic, it will change to a pink color or an orange color, or depending on what you're using. If we're just looking for what we call P alkalinity, stands for phenolphthalein alkalinity, we use phenolphthalein. It goes from clear to pink. And if you're looking for total alkalinity, there's a different, there's other indicators. There's methyl orange, which turns, like a orange to a pink. There's bromocressyl green, which turns from green to purple or purple to green. I can't remember. They just turn different colors, and reds to purples, purples to reds. You just know what indicator you're looking for. Some are real difficult to tell a color change because is it red? Is it purple? Is it going? But after time, you kind of get the hang of it. One thing with alkalinity is that you do have to dechlorinate the sample, so you have to use sodium thiosulfate because chlorine is an interference in this test. So you want to make sure that you're dechlorinating the samples. Some things, so this is kind of how it goes. You start off clear, the more acid you add, the more pink it becomes. You want to make sure that you standardize your acid when you're doing this test, because a lot of places will make up their own acid because you have to have a certain, molarity of acid. And so you're mixing acid with water. And if somebody is inaccurate, then you think you're starting with a certain molarity or a certain concentration of acid. And if it's higher or lower, then you'll get a higher or lower reading than you should be. So when you do your calculations. So the way to standardize acid is to do this titration with against a known concentration. So you can buy known, standards of alkalinity or standards of hardness. And so when you do that, you can figure out exactly, your acid might be, instead of 1 molar, it might be 0.95 molar, so you can use that and have accurate concentrations. And then you also want to, if you want to be more accurate, you can over time see if you can compare the dye indicator. So it took, this much acid to, get to our endpoint. And you can also use a pH meter. So if we know our endpoint is at pH, 6.5 or what have you, or 6.9, because that starts to get into the more acidic. You can just use a pH meter and do the titration and see if you get similar amounts to do that. So that can tell you how well you're doing your titrations. And it's also good to do comparisons between the operators, again, because you see things different, colors look different. Some people are a little heavy-handed on the acid because they want to get the test done pretty quick. And so a lot of times you can overshoot your endpoint. So just seeing how everybody does it and compares. So some issues that you can run up against, again, adding the acid too fast. So you do what's called overshooting the endpoint. So if you're just adding it and all of a sudden it goes from this, light pink color to red, you've overshot your endpoint. Right when it goes from clear to this light pink and you're swirling it and it stays that light pink and it doesn't go back to clear, that's your endpoint. That tells you that, you've completed the titration. Again, if you're using too weak of an acid, you're going to get incorrect results because it's going to look like it took more to get your reaction. So that's where that standardizing the acid comes in, knowing the accurate amount of or concentration of your acid. Not using the correct sample volume that they lay out in the method. If you have too much liquid, you could dilute out the indicators. And again, if you don't dechlorinate, that interferes with the test too. As far as turbidity goes, again, there's only one approved method for this. It's the nephelometric method. It's kind of a deviation of the old Jackson turbidity, Jackson candle turbidity method, which is what they used to use. They used to have a candle and they would have a cylinder with water, and you would look down and see, you could like kind of crank it up, crank it down, and see, when could you see the candle light, and how many cranks and stuff would it take, and that would tell you the turbidity of water, because the more turbid, the more stuff that's in the water, the harder it would be to see the candle. Now we use electronics. So what we have here is we have a lamp that kind of goes through a lens and concentrates the light. We have a sample cell which has our liquid in it. You have some of that light that gets diffracted to a detector and some that goes through. And based on a calibration, because you calibrate your turbidimeters, it says if this much light goes through and this much light is diffracted, the turbidity is this, and so on and so forth. There's different units that we typically use. One is the benchtop unit, which is right here. And a lot of surface water treatment plants, pretty much all of them have online units. So they continuously take turbidity readings and, kind of put them to your SCADA system, or you go and record them. There are handheld units, but they're not really used a lot for any type of compliance reporting. It's more process control if you needed it. Kind of like with when I was talking about electrodes, you want to standardize these and do calibrations. So there are what are called primary and secondary standards for turbidity. Primary standards are used to calibrate. So these ones you can make up or you can buy. And there's different, down here has the different kind of turbidities that you can have. So you would calibrate with, different ones, 10, 100, 1,000. This is what I think we used in our lab when we did it. But there's ones called formazine, which you can make up, but the dilutions are unstable. So, if you're making them up by yourself, they can be cheaper, but they're not very stable. Amco tends to be the go-to one that I've seen in my time in the lab, but there's also ProCal. There's secondary standards. Then if you've calibrated your machine, you want to check it again. You want to standardize it, use those secondary standards. These come sealed from the manufacturer, so you don't make these up. You just looked and use them to confirm your calibration. They do have solid state ones, but they're not really recommended. I think Hawk makes one called like IntelliCal. They're just not, they just aren't really good standards to use. So we don't recommend those. Not we as Eagle, but in the laboratory industry. So, and again, you want to check them against your primary standards at least quarterly, sometimes more often, but usually it's quarterly, so that you check your calibrations. You can check them daily if you want to, but I think quarterly is usually what's set out there. And you want to see a 15% tolerance. So if it says it's 10 and you get, 20 coming out as a, turbidity, you might want to check your calibrations again. Some things to note with the cuvette is, again, like with our colorimeters, these can get scratches in them. So there's a silicone oil that you can use that it'll fill them in. So you don't have the scratches. You want to, wipe them down before you put them in so there's no fingerprints. Cold samples can give you incorrect readings because it could be condensation, and that condensation could make the light path kind of veer off. And so it looks like it's been absorbed in the sample when really it's been, kind of deflected by the condensation. So you get an incorrect reading. A lot of these have what's called an indexing ring on it. So it's like a little arrow or a little white line on it. And if you're doing turbidity, it's good to use kind of the same cuvette through the whole reading, because if you're using different cuvettes, one might have a scratch on it, one might not. And those indexing rings, if you're using the same one, kind of always have you putting the cuvette in the machine the same way every time. So even if there's a scratch on one side, if you're always putting it in the same way every time, it's always going to read that way. You've done that for your calibrations. You've done that for your blanks. So it's not the cuvette that's causing the issue. For continuous read units, that a lot of people have, again, you can check your calibration against, with primary, sorry, I should just say secondary standards on here. And you want to check according to the calibrating according to the manufacturer's recommendations. So some say monthly, some say quarterly. And you can always compare it with your benchtop units. So you can take the same sample and you see what it is in the continuous read one and run it on the benchtop and see if they're comparable. So that helps you with just making sure everything's running right. Hardness, really there's not much to talk about with hardness. There's two ways to do it. One's by calculation, which most of us don't do because you need an atomic absorption spectroscopy machine. The other one is by titrating with EDTA. So again, another titration method. It usually goes from this pink to a purple to the blue is a final stage in that. Again, that preferred method is by calculation. So you would figure out your calcium, you'd figure out your magnesium using an ICP mass spec or an atomic absorption spectroscopy machine, which most of us don't have in a laboratory. And then you use those to get it. That's more accurate, but most of us would do a titration. Again, we're going to have some type of buffer that we put in the water. We're going to use an indicator like with alkalinity. This one we use what's called endochrome black tea indicator that turns this purple color. You also add magnesium chloride, and it's good to hold the bottle vertically instead of sideways so that you get uniform drops when you're adding that, so that the drops are all the same. Titrate with EDTA until you hit this endpoint. That EDTA kind of binds on to metals and causes this complex to happen. So you get the color. Pretty much the same things that I talked about with alkalinity are with hardness. Overshooting the endpoint, not having the correct concentration of what you're titrating with. So all the similar things. All right, coming down the wire here, and we're coming down to time. So the last ones I'm going to talk about are fluoride. The three ones that are approved for fluoride are ion chromatography, ion selective electrodes, and the Spadden's method. Ion chromatography is the most accurate and the best one, but most people do not have an ion chromatography machine. This is good for, high volume labs like contract labs, because they can do a lot of samples through here quickly. Most of us don't have this. So most labs will use either the ion selective electrode, which is an electrode, as its name says, that is selective for specific ions. There's a fluoride probe, a nitrate probe, a chloride probe. So each one has its own individual ion that it's looking for. And kind of like pH, you have a magnetic stirrer that's stirring the sample. You've got the probe and usually a reference electrode, and then you have your meter. There's a couple things with this one. You always should add some type of it's called total ionic strength adjustment buffer. It's referred to as TISAB. There's different types, but there's one that you just have to do like 1-to-1. So if you have 50 mils of sample, you have 50 mils of TISAB. There's different ones out there, but you have to do different concentrations. But it pretty much just adjusts the sample. It changes the pH. It makes the ions available to be, kind of read by the probe very easily. It complexes with things that might interfere with the method, but that is required per the method. As I talked about with other things, you want to calibrate your electrode and, bracket with the range you're going to look at. So, for fluoride, we're looking for anything from like a 0 to, usually 2, 4 is above, 4 and above is our MCL. So you don't want to do like 0, 10, 50, because we're not going to be looking for fluoride that high. So you want to make sure that you're looking in the range and make sure the slope is good and giving that electrode time to stabilize. Some of the good things about the ISE probe, you get a better range with this than the Spadden's method, because the Spadden's method can really only read to 2 milligrams per liter, and anything above that, you have to dilute the sample. So this one gives you a better range. There's fewer interferences because the Spadden's method has some common things, iron, aluminum, sulfate, phosphate that we can see in water that interfere with that one. And this one, you're pretty much putting a probe in the water and, getting a reading. Now, anybody who's used these probes are great when they work and horrific when they don't work. So I don't know about technique errors, but when these probes don't work, they can be a nightmare. Some of the cons, it's more expensive than the Spaddens method for the most part because the probes are more expensive and the meters are more expensive. And then you have equipment to maintain with this one that are kind of more finicky, let's just call it. The Spaddens method, Spaddens stands for sodium 2-parasulfophenylazole 1,8-dihydroxy 3,6 naphthalene disulfonate. Again, another one that we don't want to do a tongue twister. This is just a colorimetric method. So just like Hock's colorimetric method for the DPD for chlorine, this is very similar. The one thing in this one is when you add the reagent, actually the more fluoride that's in the sample, the lighter the sample becomes. So in most of the other ones, iron, phosphate, chlorine, those colorimeters, they become darker the more it is. This one actually becomes lighter because the Spaddens is actually reacting with the zirconium, which is complexing with the fluoride. And so it actually is kind of like sucking the color in almost when you have the fluoride in there. One thing about this one, in the method, it says that you should dechlorinate and distill the sample. I don't know many people that do that at all, but it gives you a more precise reading, but it does spell that out in the method. Spaddens does have a limited shelf life, so it will expire over time. And like I said, if their sample is above 2 milligrams per liter, you have to dilute the sample because the slope of the calibration curve becomes nonlinear, and so you don't have accurate results above 2. Again, some pros with this one, kind of less operator training because it's something that you do often with other things. So you're used to the colorimetric method. So people who don't use probes, you do have to train them on calibrating and doing different things with the probes, looking at slopes. Can be cheaper depending on what you're doing. So if you are only doing a few measurements every once in a while, it could be cheaper than the probes. Again, the probes are more expensive, but if you're doing a lot of samples, the probes can be more cost effective. You just got to look at what your lab is doing. Some of the cons, like I said, lots of things interfere with this that are common in water. Phosphate, sulfates, aluminum. So at pretty low levels, things that we would normally see in water, so they can interfere with the sample. Again, you have to dechlorinate the sample, but you can't use sodium thiosulfate, which is the one that we're most familiar with. You have to use sodium arsenite for this one. A lot of times the Spaddens comes with sodium arsenite already and kind of incorporated with it. And I already talked about diluting above 2. With that, got us in a little over time, but
Awesome,
a lot of
awesome, Amy.
material.
Yeah, thank you for taking the time. As Matt launches a final poll question, we do have one question on here related to, I think, slide number 11. Isn't the hole on the probe supposed to be plugged with the rubber stopper, except when running the test? Was the question.
Yes, that is exactly right. Yeah, so you can put it on there because then everything doesn't evaporate out. Yep, and when you're running the test. Yep, good point. Thank you.
Awesome. Thank you.
It's been about 7, 8 years since I've done this. So